welcome you all to this course on electron diffraction and imaging. In today's class we will talk about what is the need for transformation of indices when we go from one crystal structure to other, or what is transformation of indices. That is what we will discuss. Okay. In the earlier classes you have studied, okay, when a crystal structure is there, okay, we define the crystal with respect to some coordinate system. With respect to that coordinate system, okay, any direction in the crystal can be written in terms of r equals u into a plus v into b plus w into c. Similarly, okay, then the indices of the planes HKL, if you wanted to represent, okay, the planes, and this is the way vectorially we will represent. Otherwise normally we represent these directions with the coefficients of these vectors. This is how it is being done. This is for a specific direction. If you want to represent it for a family of directions, then this is the way we represent. No, sorry, this will be with respect to, correct, right. So, if you wanted to represent a plane, generally we represent it with respect to HKL, okay, specific plane, and family of plane is with respect to HKL, and this HKL are nothing but, if you take a vector r star in the reciprocal lattice, it will be h into a star plus k into b star plus L into C star, correct. What one should remember is that all these vectors are written with respect to a specific coordinate system chosen, correct. That is how we define it. But we also learned in the crystallography that the unit cell itself is not unique for any crystal structure. That means that we can choose different type of unit cell, correct. So, because of the non-uniqueness of the unit cell, okay, we can have different coordinate system to represent each unit cell. Okay. Quite often we find that in phase transformations we may have to use different types of unit cell to represent, okay, the same crystal structure, because sometimes it is easy to work with another type of a unit cell. But normally what happens is that conventionally we use the unit cell which represents the full symmetry. That need not be the case always. Okay. For example, here this two-dimensional lattice which is shown, we have different types of unit cells which we can have. Okay. All of them, okay, represent the periodicity in the lattice, right. By keeping one adjacent to each other, we can generate the, in this case, a two-dimensional lattice. It could be a primitive unit cell or it could be a non-primitive one. The examples is that we can have an HCP, okay. HCP itself can be represented in terms of orthorhombic. Similarly, FCC we know that can be considered as a tetragonal unit cell which C by A ratio equals 1.414. So, these sort of situations are always there, and in many phase transformation also, like FCC, when a transformation takes place, it can go into orthogonal orthorhombic structure. Similarly, in from FCC to orthorhombic structure, transformations can take place, okay. FCC to tetragonal, rhombohedral to hexagonal, okay. There are various types of, especially for rhombohedral to hexagonal, what it happens is that it is only a convenience for which sometimes we can represent in rhombohedral coordinate system, or in some cases you can represent them in terms of hexagonal coordinate system. Okay. So, today we will talk about, if we represent it in one coordinate system or another, how the indices of the planes and directions will change. That is very important. Okay. Let us take a two-dimensional, that is, this is a disordered hexagonal lattice which we are showing, okay. And in this as well as in this, if you see it, it is the lattice translation vectors which is being shown with angle between them 120 degree, okay. In this particular case, you assume that an ordering is taking place. It transforms into an ordered lattice. Now, if you look at this ordered lattice, okay, atoms are occupying specific positions. If you look at the unit cell, this will be the A lattice parameter. This is going to be the B lattice parameter. Okay. Now, what is essentially happening is that the unit cell is essentially, in this case, has become a rectangle. Okay. So, when we represent the ordered lattice, we are going to represent as a rectangular unit cell. When we represent the disordered lattice, we are going to represent it as a hexagonal unit cell. Okay. And in these lattices, suppose you take diffraction pattern where that you have both the structures. Now, how are you going to index them? Okay. Then you should understand which plane will change into which plane in the ordered lattice. This is what this transformation of indices help us understand. This is another example where it is on a hexagonal lattice. Okay. It is essentially transforming into another which is an ordered, which is hexagonal, but in this specific case it is only the lattice parameter as double. Okay. That is as far as two-dimensional lattice is concerned. We can take the case of a three-dimensional lattice. Here I have taken an FCC lattice. Okay. We assume that this is an FCC lattice. Okay. In this lattice, we are showing a unit cell in this specific case. Okay. The lattice is essentially infinite. Okay. Atoms, we assume that it is an alloy which contains two types of elements. Okay. We cannot distinguish which atom occupies which position. So, we call it as a disordered one, chemically disordered one. Okay. A case which I have considered where an ordering is taking place, and the unit cell of the ordered lattice which is being shown here. In this specific case, if you look at the unit cell, okay, it is as if two FCC lattices are kept on top of the other. Okay. And then in this direction as well as in this direction, that is A and B, the lattice parameter remains the same. C direction, the lattice parameter has doubled because one is kept, and some ordering has been introduced at specific positions. This is essentially a body centered tetragonal structure. Okay. Similarly, we can consider another structure, okay, where it is going from FCC to an orthorhombic unit cell. So, these sort of phase transformations are quite often seen. Okay. We will be getting diffraction pattern due to the ordered lattice as well as the disordered lattice. Okay. So, there are ways in which and these type of transformation when they occur, there is some orientation relationship between the lattices. Because of that, we can index the diffraction pattern either in terms of the FCC lattice, or we can index them in terms of the ordered lattice also. But in both the cases, the same point we will be representing with two types of G vectors, depending upon which whether we have chosen the ordered lattice or the disordered lattice to represent. I have mentioned already that unique cell is not unique. Okay. Here what I have shown is that same the case which I have considered in this specific case is the body centered tetragonal unit cell which I have taken. Okay. I had just shown the diffraction pattern corresponding to it. If you see in the literature, this diffraction pattern, the spots could be, this spot could be indexed as 200, these will be indexed at 020, these are all fundamental reflections. Okay. The same fundamental reflection 002, okay, for the body centered tetragonal, the fundamental reflection will be 004. Okay. But as far as matrix is concerned, FCC, we represent it as 002. Okay. Similarly, the 001 is represented 002 of the ordered lattice. Similarly, that in terms of matrix or the FCC lattice, if we represent this specific spot, we will represent 10.5, which in terms of ordered lattice it will be represented as 0101. Okay. So, this from looking at this we can make out that some correspondence is there, but is there any procedure by which we can determine this? This is what we are going to discuss in today's class. Okay. This is just an example to show what is the need for it. Okay. So, FCC to tetragonal is one which transformation which we have considered. Another, I mentioned that this is not a unique one. Okay. Now, before we go into the procedure, the general procedure, let us take it with just an example. This is again a hexagonal 2-dimensional lattice which I had shown. In this lattice, okay, this is the A lattice parameter, this is the B lattice parameter, which is nothing but equal to A, the same as A and B are equal, and angle between them is 120 degree. This is how we represent a hexagonal 2-dimensional lattice. Okay. This same lattice can be represented, but this is a primitive one, hexagonal lattice, and we can represent it as a C-centered rectangular lattice. So, in the C-centered rectangular lattice, if you see the lattice parameter, this is A and this is B. Okay. So, in terms of this lattice parameter, in terms of the rectangular lattice, okay, we wanted to represent in terms of the hexagonal lattice. How we will go about? This A will be written as 2A plus 1B, okay. B will be represented as 0A plus 1B. This is how, this is the, in that terms of rectangular lattice, this is in terms of the hexagonal lattice. In terms of hexagonal lattice, we are writing the coordinates, okay, of the rectangular lattice in terms of the hexagonal lattice. Okay. We can do it the other way around also. Okay. So, then what will happen is that A will be equal to half into A minus half into B. Okay. B will be equal to 0 into A plus 1 into B. Okay. That means that when we wanted to represent hexagonal lattice in terms of the rectangular lattice, these two cases, if you look at the type of equations which we use, they are not the same. Okay. Let us take a generalization. So, essentially what we are trying to do it is that in any lattice, if we consider A, B, C are the coordinates which represent the unit cell, okay, vectors, then this is for one lattice, and the original lattice, or it is the coordinate of the unit cell of the transformed lattice in terms of the old lattice we wanted to find out. Okay. Then this can be written as this is, I am just writing it in terms of, so M1, M, these are all the coefficients. Okay. This I am writing it so that it can be written in a matrix notation, that is all. B will be equal to C. Okay. So, that means that like here what we have written 2 and 1 and 0 and 1 are the coefficients. Similarly, we have taken some coefficients like this. So, this can be written essentially as M22, M23, M31, M32, this way we can write, this is right. Similarly, we can see that when the old coordinates we wanted to represent in terms of the new one, then these indices are not the same. So, we can use a different symbol to represent it. So, then it will happen A will be equal to, I will write into C n 3 3 into C, correct. Here now if we represent A, B, C, this will be in terms of n11, n12, n13, n21, n22, n23, n31, n32, n33. You can write it in this form, correct. So, these are two different matrices. Okay. Now, suppose I wanted to represent this in terms of ABC. Now, this ABC, if I substitute this one, what it will happen? Suppose this matrix I put it as M and this I write it as N. Okay. Then what it will happen is that this ABC will come in terms of M into N into ABC, it will happen, correct. That means that nothing but M into N equals I an identity matrix, in which case it can happen is that when they are inverse of each other, correct. That relationship comes from here. Okay. So, this what we have looked at, it is only the transformation of the coordinates which we have looked at it, how we can go from one coordinate system to the another, write it. But what essentially we have to consider is that in this particular case, if you take a vector R, the vector R irrespective of whichever is the coordinate system which we choose it, that remains that same vector. Okay, it is magnitude. So, now we can represent this same vector, okay, as R equals in the old coordinate system, and in the new system suppose we wanted to write this R equal to U into A, okay, plus V into B plus W into C, we can represent it, okay, correct. What we can do it is, this essentially means that this equals U into A B plus W into C, correct. This is what it is valid, irrespective of which coordinate system which we choose, the vector has to be the same. Now, we can substitute for ABC, okay, in terms of the old coordinate system, and if we equate the coefficient of A, B and C, then we can find out the value of U, V and W in terms of this equation we can find out, correct. Okay. That part of the substitution I am just not doing, okay, but I will give you just what the value is going to turn out to be, okay. This is what essentially it will turn out to be. Okay. What essentially, or we can just try to cross check whether it is right or wrong, so that we do not make a mistake. Okay. I can substitute for here U into, okay, A I can substitute in terms of M11 into A plus M12 into B plus M13 into C plus V into M21 into A plus M22 into B plus M23 into C, okay, plus W into M31 into A, M32 into B plus M33 into C. Okay. If we take the coefficients of A alone, okay, then what it will happen? On that side it is U, small u, it equals, okay, M11 into U plus M21 into V plus M31 into W, correct? Is it right? Okay. So, now similarly we can write it for V, which will be M12 into U plus M22 into V plus M32 into W. This is V, W equals M13 into U M23 into V plus M33 into W. From this we can get this expression. Okay. This is clear? Okay. Similarly, we can get it in terms of the U, V and W. In terms of small u, v, w we can find out. But what is essentially is going to happen is that now A, B and C we are going to substitute with this equation. Okay. Now what it will happen is that in that case will be N11, N21, N23, N12, N22, no, N31, N32, N13, N23, N33 into small u E w. This is how it will turn out to be. So, when we have to, for a direction, if you see with respect to what we have taken for transformation from here to here, okay, from that is from the old axis to new axis when we come, okay. Here for the direction in the new one, it is in terms of this, you can understand, it will be essentially nothing but a transpose of one of the other, okay. Is this clear? Okay, because here what we have done is substituted for A, B, C in terms of this one. Now we have found out what is the relationship. This is with respect to, similarly we can find out relationship between planes also, okay. In the case of a plane, what will happen is, I will just write down the, if it is in the new coordinate system, HKL, capital HKL represent the indices of a plane, okay. This will be equal to This is going to be the same as that for the coordinate system for the plane. Okay. Similarly, for small HKL, this will turn out to be N22, N23, okay. This is how it will turn out to be. Okay. Is essentially, since for the case of going from one lattice to other, when we wanted to find out the transformation of indices with respect to a direction, okay, we chose a vector in the space in which the lattice is defined. But HKL is essentially nothing but coefficients in reciprocal lattice. Now you take a vector in the reciprocal lattice, okay, like the way we have defined it. Okay. If we use this vector, okay, how exactly it can be done is that this is in terms of this lattice, correct? Similarly, we can define a vector in reciprocal space also. If we choose that, okay, for both the lattices, whichever be the indices which we have used, both will have two types of lattices which will be there. Then essentially what will happen is that suppose we take H into A star plus L into C star. This is all in capital which we have taken. Okay. With respect to which, if we take a dot product with respect to A, okay, then what will happen? Okay. See, this will be getting some value, correct? But similarly in reciprocal lattice also, okay, no, sorry, this is H, this is K, the coefficients have to be L, correct? And with respect to the old lattice, the reciprocal lattice vectors will be H into A star plus K into B star plus L into C star, correct? So, these two vectors this has to be the same in reciprocal lattice also, because the way we have transformed from in real lattice from one unit cell to another, similar way in the reciprocal lattice also we will have corresponding to old lattice one unit cell of reciprocal lattice, and for the transformed lattice also there will be another reciprocal lattice. A vector has to have the same magnitude, that does not change, right. So, we can write an expression like this, and if we take a dot product of this with respect to A, and we take a dot product here also, on this side also we have to put A to take a dot product. Now, if we substitute, okay, what is essentially is going to happen is that this A can be written in terms of the old coordinate system, then we will be finding that value. Here what it will happen, A star, this will turn out to be only H, the rest of the terms will not be there. So, from this expression we will be able to derive this. This part of the derivation I am not going into the detail, this you can do it, this is how the final formula comes. So, now essentially you have got transformation matrices, okay, for going from one unit cell to another for direction as well as for planes. Is it clear? Okay. This can be used to go from one lattice to the another, we can find out the transformation of indices. Okay. Let us just take one example. Okay. That what we will do it is, from a simple hexagon it transforms to an orthorhombic unit cell. Okay. So, if we come back to this lattice which is shown in this slide, okay, this is essentially a hexagonal lattice. Okay. A, B, okay, we have defined it, and if we assume that next layer is kept on top of it at a distance c, then it forms a simple hexagonal lattice. Okay. And here this is A and B lattice for a rectangular lattice, and the c direction remains that same, then it becomes a orthogonal, not orthogonal, orthorhombic. Okay. This becomes an orthorhombic lattice. So, it is a hexagonal to orthorhombic lattice which is going. If you look at the expression for A, B and C, what it will turn out to be? Okay. We have written this expression. Okay. Here it will become 1 into C, correct, for this lattice. Here also what it will become? B is, no, A will be, this is 0 into C, because the 0 direction there is vector A, when we represent it there is no projection, correct, no component of A in the, because it is in the basal plane, correct. Here it will become 0 into C, and what will happen to C? 0 into A plus 0 into B plus 1 into C, correct. So, now this matrix, if we look at it, A, B, C, this will turn out to be 2, 1, 0, 0, 1, 0, 0, 0, 1 into A, B, C, correct. Similarly, we can do a substitution here. As far as the A is concerned, there is no component in. So, this will become 0 into C, this will become 0 into C, and the small c will be 0 into A plus 0 into B plus 1 into C. So, this, if we look at it, A, B and C will turn out to be half minus half 0, 0, 1, 0, 0, 0, 1 into, this is how it will turn out to be, these two equations. Okay. This is one. This is the equation for going from one coordinate system to the other, okay, hexagonal to rectangular, the orthorhombic, or from orthorhombic to hexagonal. Okay. Now, planes, we know that how it has to be indexed. Okay. If we know, suppose we wanted to find out HKL, HKL also is the same matrix which works, will be equal to correct. Suppose we wanted to find out, okay, 1 0 0 plane in this lattice, hexagonal lattice, then what it will happen? For then HKL will turn out to be 2 1 0 0 1 0 0 0 1, correct. What will HKL will turn out to be? 2 0 0, correct. That is HKL. This will turn out to be 2, correct. Yeah, or H will turn out to be here 2, K will turn out to be 0, correct. L will turn out to be 0. Okay. We can take another one, that is, suppose we wanted to take 1 1 0. Now what it will happen? H will turn out to be 2, K will turn out to be 1, L will turn out to be 0. So, 1 1 0 in hexagonal lattice will be represented as 2 1 0 plane in the orthorhombic lattice. So, this is how we can find out correspondence between planes. Similarly, we can find out correspondence between directions also. Okay. So, that I want you people to work it out as an exercise. Okay. This you can think of various planes one can choose and try to find out how correspondence. In fact, for any crystal structure, okay, similar type of correspondence we can find out. This is we have initially took for a 2-dimensional case, now we extended to a 3-dimension. Similarly, for all the lattices, okay, when you know the unit cell in one and how it is oriented with respect to that, when it transforms into the other lattice, we will be able to find out direction. And this method is what is used here to represent these planes in the ordered and the disordered lattice. Okay. Is it clear? Okay. Similarly, I mentioned about that another case, okay, like from that is from rhombohedral to hexagonal, because sometimes in some cases the rhombohedral has to be expressed in terms of hexagonal lattice. That also you know what the coordinates of rhombohedral are. If you use a hexagonal lattice, okay, what will be the coordinates? One can write the transformation matrix to go from one coordinate system to the other. Okay. Then using these formulas which are written for directions as well as for the planes, one can immediately find out the correspondence between the planes and directions between the two lattices. In fact, this formalism could be used to find out direction between planes in one coordinate system to another coordinate system, okay, in any type of transformation. Okay. Most of the time we will see that in ordering transformation is essentially where, okay, the atoms are replaced at some positions in the disordered lattice, okay, and then an ordered lattice forms. When that ordered lattice forms, it could have a symmetry which is lower than that of the disordered lattice. Okay. Not only that, it can have the lattice parameter which could be either the same as that of the ordered lattice or that of the disordered lattice, or the lattice parameter could be more. Okay. This sort of transformation could occur. Okay. So, in all such cases, using this formalism, one can easily find out the correspondence between planes and directions, and this is very much necessary, okay, when we wanted to index diffraction patterns in terms of either in the matrix in terms of the disordered lattice or in terms of that ordered lattice. Okay. We will stop here now.